Okay, in this problem we're told that there are two vectors that has units of meters, so these might be some displacements that you could make by walking around on the ground. Two vectors d and e. We want to find the magnitude of the vector given by 2d minus e. We also want to know the angle that it makes with respect to the x-axis. And you can see in this image we have a visual sense of what these vectors do. So before we even start to work out any of the numbers, let's get a visual idea of what it should look like if we determine the vector f, which is 2d minus e. So you see the vector d is already drawn there. If I wanted to figure out what does it look like to have 2d, I would simply take d and I would add to it again using the tip to tail method. So if I added another one, I should find a vector that ends up at twice the height and twice the width. In other words, it should end up at 12 I hat and 6 j hat. In other words, it would end up somewhere about here. So that would be adding another d, and so this whole vector would be 2d. The vector e, you can see it points down and to the right, but if I was interested in figuring out what minus e looked like, minus e would be represented by a vector that pointed the opposite way. In other words, it would look like this, a little bit longer though. How would I show that? What happens if I take that vector and I stick it on to the end of the vector 2d? I would stick it to the tip of that vector, and I would simply send it along, following over 4 spaces and up 5 spaces. And so this thing would end up somewhere about here, approximately. That vector that I've just shown you is the vector minus e. And so in the end, if I take 2d and I subtract e, then the final vector I get should point from the tail of the first vector to the head of the last vector. In other words, that's what we should find. The vector 2d minus e should be in that first quadrant and point up in that direction, approximately. So in order to work this out, let's figure out how to do the subtraction with the unit vectors involved. 2d minus e, writing it out with components, this is 2 times the vector 6.00 I hat plus 3.00 j hat with units of meters. And then I'm going to subtract, I'll put that down here, subtract the vector e, which is 4.00 I hat minus 5.00 j hat meters. The reason why I'm lining up the components this way is that that's how you have to add or subtract vectors. You have to subtract like components from each other. On the top, we've got 2 times 6 is 12 minus 4. That gives me 8 I hat. Then we have 2 times 3 is 6 minus a minus 5, which is really plus 5. So this should be plus 11.00 j hat meters. So that's what the vector f is. The vector f should look like this, and that is approximately what we sketched before. We would simply want to find the magnitude of this vector and the angle it makes with respect to the x-axis. So to get the magnitude f, which is the abbreviation we use for the magnitude of this vector, f, it should involve the sum of the squares of the various components. Since it's only a vector that lies in a plane, we only need to worry about 2 components, its x and its y components. And so this would involve the square root of the sum of the squares, square root of 8 meters squared plus 11 meters squared. And when you work that out, 13.60, the meters are the only thing that's left over because meters squared with a square root gives you meters. And we can approximate that as 13.6 meters. The last thing to do is figure out what is the angle that it makes with respect to the x-axis. And just by staring at the picture I drew, I'm kind of expecting that this angle theta should be somewhere around 40, 50, 60 degrees or so. It would be bizarre if it was bigger than 90 or less than 0. So let's work this out. What we just realized was that the vector f was written in the form 8i hat plus 11 j hat meters. Okay. The vector, which we could draw like this, has components where this side length is 8 and this side length is 11. And if we're interested in figuring out this angle, then we just have to use one of our favorite trig functions. You could use tangent, you could use cosine, sine. I'm going to go ahead and use sine just for fun. The sine of theta is the opposite, which is 11, divided by the hypotenuse. That's the number that we've previously determined. The hypotenuse was 13.6. In fact, I'll leave it as 13.60 just for purposes of calculation, keeping an extra digit around just until we're ready to round at the end. That tells you, these are meters, they cancel. That tells you that theta is the inverse sine of 11 over 13.60. Okay? The meters cancel. What you get, the inverse sine is 53.98 degrees, and I should round this to 3 sig figs. So that's 54.0 degrees as measured with respect to the x-axis.